Rosie!
Hello everyone, this is Gavzar, welcoming you to a very special edition of Physics Detective. Be advised there may be some spoilers ahead. Well, today is the day that we welcome Marty Mcfly to the future. Today I'm talking about the infamous recipe. 1 flux capacitor plus 88 miles per hour plus 1.21 gigawatts equals time travel. Specifically, I'm focusing on the third part of that equation, 1.21 gigawatts. In moving forward, I'll be assuming that gigawatts is Doc Brown's quirky pronunciation of the word gigawatts. We have a lot to talk about, so let's get started. The flux capacitor is nuclear-powered, first using some kind of fission reactor with plutonium-239 as the fuel, and later using Mr. Fusion with garbage as the power source. So let's first address the question of what is nuclear energy and how can it be harnessed. We'll start with fission energy. As you may know, the center or nucleus of an atom is made of protons and neutrons. You may also probably know the old adage that opposites attract. Inversely, similar things repel. Protons, all having identical positive charges, repel each other. This has two important consequences for our discussion. First, it takes energy to bring protons together to form atoms. And second, it also requires a force to hold the protons together once you have formed the atom. This force is known as the strong nuclear force. To use an analogy, bringing protons together and keeping them together with the strong force is a lot like bringing similar ends of magnets together and holding them together with glue. Notice though that if we hit the magnets hard enough, then we could break the glue holding them together and the magnets would fly apart. The same goes with atoms. If you hit them hard enough, you can break the strong force bonds that hold them together and the pieces fly apart. The problem is that the isotopes of most atoms are so tightly bound that it takes so much energy to break them apart that it isn't worth it to try. There are a few notable exceptions to this, including uranium-233, uranium-235, and plutonium-239. What makes them so special is that first, it doesn't take much to break them apart, and second, when they break apart, they tend to break into two large pieces with some neutrons left over. These ejected neutrons then have enough energy to break apart nearby atoms. These atoms break up in similar fashion to the first, ejecting neutrons that go on to break even more. This is what's known as a chain reaction. So now the important question is, how do we go about converting nuclear energy into electrical energy? As we just saw, nuclear energy, or what is sometimes called nuclear binding energy, is energy that holds atoms together, and that it will send fission pieces flying when the bonds are broken. These fragments fly around, bumping into other atoms and sending them into motion. On macroscopic scales, we experience this kind of motion as heat. So, as far as nuclear power is concerned, nuclear energy is heat energy. With that in mind, let's look at two different ways that heat energy can be turned into electrical energy. First, most nuclear power plants in operation today are water-cooled reactors with the fuel arranged in rods. As the fission reaction is sustained, these fuel rods heat up. Cold water is then pumped through the reactor, absorbing heat from the rods as it flows through. For radiation safety reasons, this water is never allowed to see the light of day. Instead, it flows through what is called a heat exchanger. The heat exchanger is set up such that the heat in the hot water coming from the reactor is absorbed by a second line of cool water. By the time this second line of water exits the heat exchanger, it has already boiled and become water vapor. This boiled water is then sent through a turbine. In the turbine, the heat and pressure of the steam is used to turn an electric generator. Now this second loop is what's called the Rankine cycle, and it happens to be the same thermodynamic cycle used in coal-fired power plants. Anyway, at this point, there are a few questions that need answering. First, we need to know if there is enough energy in the amount of plutonium that they use to fuel the flux capacitor. Now we know that it uses 1.21 gigawatts, but this is a measure of power and not energy. The difference is that power is a measure of energy consumption over time. Let's use an analogy to better explain the difference between power and energy. Let's say that Marty wants to go backpacking through the desert, and he knows that he needs to drink 5 bottles of water a day to stay hydrated. So then, will he be fine if he takes 17 bottles? Well, the obvious answer is that it depends on how long his trip is. So for this example, water per time is equivalent to energy per time. Also, just as we need to know how long the trip is in order to figure out how much water is needed, so too do we need to know how long the flux capacitor needs this supply of 1.21 gigawatts. To answer this question, we'll use the fact that it can be powered by a bolt of lightning. The average bolt of lightning lasts a mere 30 microseconds. So 1.21 gigawatts times 30 microseconds gives a total of 36.3 kilojoules of energy. Now if we consider the amount of energy released by the fission of a plutonium atom and its weight, we find an average energy density of 83.6 billion kilojoules per kilogram. What this means is that the flux capacitor needs a minimum of 434 nanograms of plutonium. To put this into perspective, 434 nanograms of plutonium metal would make a ball smaller than a fine grain of sand. There is one fairly large detail that we need to address, though. You may have noticed that I said it would take a minimum of 434 nanograms. I say minimum because the laws of thermodynamics are such that only a fraction of the heat energy released in the plutonium can be converted into electrical energy. The exact efficiency of the conversion depends on the setup and complexity of the system. But for the simple kind of configuration that would be needed to fit in and on the DeLorean, we expect an efficiency of around 33%. Accounting for this increases the mass, but it's still only a tiny fraction of the mass of the plutonium billet that they used. So far, we haven't seen anything that tells us that the Back to the Future time machine is infeasible. So let's take a closer look at the turbine. The amount of electrical energy produced is dependent on a number of factors, including the temperature and pressure of the steam that enters, the pressure at the outlet, and, most importantly for this phase of our analysis, the rate at which the steam is flowing through. By assuming some reasonable values and ideal behavior, we find that the turbine would have to process an astounding 2,700 pounds of steam per second. Now, this doesn't mean that there needs to necessarily be 2.5 tons of water and water vapor on the DeLorean. Instead, a much more reasonable amount of water, say 270 pounds, could be used. However, it would cycle through the system 10 times in a second. In either case, and virtually any other case in between, there are challenges that are virtually impossible to overcome. So at this point, it's safe to rule out the Rankine cycle for use in the DeLorean. So let's look at the other method for converting fission heat into electricity. When two different metals are joined together to form what is called a thermocouple, a voltage will form if one end is hotter than the other. So in theory, the plutonium could be switched into a supercritical configuration that would cause the temperature to spike. Thermocouples attached to the plutonium would then begin to heat up, creating a voltage that could be used to power the flux capacitor. There are two main drawbacks to this approach, however. For one, the thermocouples are very inefficient, being able to convert only 3 to 7% of their thermal energy into electrical energy. This isn't so bad, in that the minimum number of atoms needed to fission would still be smaller than a grain of sand. Another drawback to this method is that while the plutonium can heat up quite rapidly, it takes more time to heat up the thermocouple, especially if you don't want to damage it. That being said, the drawbacks to this method are arguably far less significant than the drawbacks to using the Rankine cycle, and so it's likely that Doc Brown went with thermocouples. Before we end, we need to talk about fusion power. At the end of the first film, Doc Brown has returned from the future, having upgraded the DeLorean so that the flux capacitor is powered by a mini fusion reactor rather than a fission reactor. As we have seen, fission means splitting atoms apart. Fusion, on the other hand, means putting atoms together, and here is how it works. As mentioned earlier, atoms are like magnets glued together, and there are two competing forces at work inside the nucleus. The electromagnetic force, which tries to push protons apart, and the strong nuclear force, which binds nucleons together. We also mentioned, or at least hinted, that the purpose of neutrons is to help find a balance between these two competing forces. If an atom has too many or too few neutrons, the result is an unstable atom that will radioactively decay. Additionally, even among stable atoms, the balance isn't quite perfect, because you can't have half a neutron or a tenth of a proton or so on, and so some atoms are more stable than others. The reason that we're talking about stability is that when two atoms are fused together, and the result is an atom that is more stable than the two that were brought together, then some of the energy that had been used to bind the atoms is released. On the other hand, if the product is less stable than the atoms that you started with, then the entire process will require more energy than you get out. What this means for Mr. Fusion is that in order to produce power, he would have to sort through the trash that Doc Brown has put in him and select combinations of atoms that can fuse to form more stable products. In the end, it is entirely possible that Mr. Fusion won't have enough viable building blocks to work with, which means that using him could be rather hit or miss. That being said, Doc does seem to sort through the trash as if selecting items that he knows are rich in atoms that Mr. Fusion can put to work. Now we could try and calculate an efficiency for Mr. Fusion to see just how much garbage would be needed, but doing so would require knowing what isotopes are in the garbage that he selects, how much garbage there is, and most difficult of all, what fission reactions are taking place. The list of reactions that could potentially be used is far too long for me to handle alone, and so that's a job that I'll leave for you. At this point, we're just about out of time, so I'll leave you with one of my traditional endings. If you like this video, then hit like and then subscribe to my channel if you haven't already. Now, I've done my best to try and explain the physics behind nuclear energy, but if there are things that were unclear, or if you want to learn more, then leave a comment below, or if you prefer, you could email your questions to gowsar@yandex.com. You can also use this email to send me suggestions for future episodes. Lastly, you can follow me on Facebook and Twitter, where I post updates on videos and have been known to post polls about what you'd like to see next. Once again, this is Gowsar, the self-proclaimed physics detective, signing off.